Hello and welcome. I'll start by providing a high-level explanation of the presentation title, Using Advanced Detection Models with eIQ Portal, and this will more or less serve as the agenda of this presentation. Now, if you're not a data scientist, I suppose that any detection model can seem advanced, but from our perspective, advanced detection models represent the state of the art to deliver best performance, accuracy, and flexibility. With this in mind, we'll walk you through the historical aspect of detection model evolution, leading up to advanced detection models, including CenterNet. In this scope, advanced refers to a combination of higher performance and accuracy, as well as functionality. Now, regarding the eIQ portal, we'll assume that you've already learned about this technology, so we'll only present a high-level perspective of this NXP tool and discuss how it allows you to train and deploy advanced neural network models. During this video, you'll hear from Ovez and I, and for a brief introduction, I'm Marcus Levy, working at Ozone Technologies and as an advisor for product development and marketing. I'm joined by Dr. Ovez Garcia, who is a senior machine learning developer also at Ozone Technologies. With this presentation, we're targeting embedded developers, not data scientists, so we'll try to avoid discussing too many details of object detection models and how they work. On the other hand, even though some might prefer to have a black box approach for machine learning and AI, we think it's helpful to understand some of the basics because ultimately you'll have to make some choices for your own application. Object detection models look within an image or video frame to find and locate a subset of object classes. Usually these models are pre-trained with public datasets to establish a high-level generalization. The most popular public datasets are, for example, VOC, COCO, and Open Images. COCO Images contains some 330,000 images representing 80 object categories, and it also includes 250,000 people with key points. VOC has about 10,000 images in which each image contains a set of objects out of 20 different classes, making for a total of about 25,000 annotated objects. Open Images contains 16 million bounding boxes for 600 object classes on 1.9 million images, making it the largest existing dataset with object detection annotations. It even includes 478,000 crowdsourced images with over 6,000 categories. So you can see that these datasets are great for generalizing, but you'll still most likely need to bring in your own training data so the model can learn new categories. However, the training will typically be greatly simplified by using transfer learning as opposed to training the model from scratch. As an embedded developer, you should approach detection with eyes wide open and understand how to cope with the challenges. In comparison with classification, detection can be quite processing intensive. For training your model, as well as collecting and labeling your data, keep in mind the camera target distance and the object size. Naturally, objects further from the camera will be smaller, so you'll have to consider resolution. Regarding object size, as the input moves through the model layers, outputs get smaller, but the number of features increase. In other words, as feature maps increase, spatial resolution is reduced until the end when the object is identified. If the object being identified is small, it's important to identify it in earlier layers before details are lost. And typically, a feature pyramid network, or FPN, can provide kind of a cheat where the downscaled image is scaled back up to increase the features. Another challenge relates to shapes and orientations. Check out the example on the right, demonstrating the challenge of getting your model to comprehend different orientations. For example, bikes on the road versus bikes hanging up on a wall. Now, many of the challenges I've pointed out can be resolved using data augmentation, and eIQ Portal contains a great augmentation tool. Just add your labeled data and push go. Another challenge is understanding which operators the device supports. This is something that we encountered when porting CenterNet and had to make modifications internal to the model architecture in order to get it to run on the i.MX 8M Plus's NPU.
Hello everyone, and thank you so much, Marcus, for this previous introduction. So when using YOLO or SSD, instead of running the model over and over across the input image with a sliding windows approach, you kind of flip it upside down and run the image through the model and pull off region of interest at different stages of the model. Different stages are important to reflect on as the input progresses through the model. Note that the spatial resolution is shrinking because the convolution operations. So if your bounding boxes are always the same size, when the image is very small in the last layers of the model, the boxes are much larger in comparison, and vice versa. So YOLO and SSD make predictions simultaneously for both localization and classification. The processing steps are also somewhat similar. It starts with the feature extraction, which we'll explain more in detail on next slides. Then it uses predefined anchor to establish the bounding box locations and then perform regression of boxes to establish probabilities based on a user-defined threshold. In other words, for a given bounding box, how confident is the algorithm that it contains an object of interest? Finally, in one of the final steps, the algorithm performs non-max suppression as a post-processing task, which is kind of a low-pass filter to get rid of noise by removing the boxes that have low probabilities score and higher overlapping. The diagram here shows an SSD algorithm connected to a feature extractor, which we'll explain more detail in future slides. So each layer of SSD algorithm handles different resolution as the input image goes through. So the top arrow, for example, represents the blue one represents a backward connection to catch high resolution features. So this process is needed because the appearance of the interest objects is lost when going deep into the model. The feature extraction process mentioned in the previous slide is done by what is also known as the backbone outcome. Classification model, for example, MobileNet or ResNet, generally contain two parts, the backbone and the classification header. So, complete classification models need the output or classification header to provide the inference results. This output is typically done by combining the average pooling and softmax layers, which assign a probability distribution or probability vector to the input data. On the other hand, when using detection models, the process is a bit different, since the classifier header won't be needed anymore, given the output of the feature extractor or backbone feeds directly into the detection section, which is also known as detection heads. To help explain backbone and detection boxes, think of the analogy using a tree. The backbone is the tree trunk. The ground can be the input image and the leaves are the bounding boxes. Every branch of the trunk is deeper and deeper into the model, and each one gives you a possible box. On the other hand, there are many choices when it comes to selecting a backbone for a detection model. Although some detection models are designed with specific backbones, for example, YOLO is typically connected to a darknet backbone, SSD is typically associated with MobileNet, CenterNet has a bit more flexibility, and a backbone such as ResNet can be selected based on the performance and accuracy requirements. Typically, you can find free backbones in public model zoos that come pre-trained with datasets such as ImageNet, so you won't have to train them from scratch. Let Google and others do this heavy lifting on their massive cloud-based machines. However, you also may want to do a little fine-tuning with specific datasets for your application domain. So the eIQ portal is a very good tool for doing this. A key step on detection model is the post-processing algorithms, usually NMS, where all the boxes with low probabilities and higher overlapping are pruned from the outcome to produce a clear detection output. The left image shows a lot of detection boxes around the cat and around the dog. Each box has a different probability. If we apply NMS over the detection list, remember all the objects belonging to the same class with higher overlapping and lower probabilities will be removed from the prediction list, and the final result will look like the image at the right. Well, now dig into some detail on specific algorithms. I think most people will be familiar with SSD, for when combining with mobile net is one of the most popular networks these days, at least for general benchmarking purposes. As we indicated previously, SSD relies on a set of predefined anchors from which are derived the bounding boxes. As you saw in the previous slide, NMS is used to help reduce the unnecessary boxes from the prediction list. Think of in this way, every bounding box is associated with a list of flavor, such as a person or a boat, and the probabilities score. These scores are derived from the classifier part. If each bounding box contains an object with an associated list of labels and probabilities, you can set a threshold value to eliminate bounding boxes that have low probabilities and also higher overlapping. As an extreme example, the blue bounding box in the image above, we have all the labels but with low scores, and hence will be suppressed from the prediction list by the NMS algorithm. As shown here in the diagram on the left, the SSD model uses a series of convolutional feature layers to allow for feature detection at multiple resolution scales. However, for best results, you should use special augmentation techniques to handle small objects that would otherwise disappear in the last layer of the detector. For example, you could customize the data augmentation pipeline to distort color channels or distort the image geometrically.
The first version of YOLO was published in 2015, and it represented a big step forward for object detection. You can see from the chart above that its evolution has brought numerous feature, performance, and size enhancements. I won't go into further detail here, leaving it up to you to seek out the plethora of papers on these models, but I do want to point out a few things. First, all YOLO versions have tiny versions, which use reduced resolution scales, possibly reducing the accuracy somewhat, especially for smaller objects. Second, I guess it's obvious to state that you should always try to use the latest version, assuming that the implementations are stable and the target device supports all the network's operators. It's for these reasons that most commercial implementations are still using the fourth version. Generally speaking, YOLO will deliver higher accuracy than SSD, but one of the issues is that YOLO is more or less married to specific backbones, such as CSP Darknet 53. So if you want to use MobileNet as your feature extractor or backbone, the YOLO model will require architectural modifications to link them together. Now, one good feature of YOLO is that the number of anchor boxes that you set as a hyperparameter will determine the number of layers used to detect objects. The next slide highlights some of the disadvantages or challenges with using YOLO and SSD. As we've mentioned before, YOLO and SSD utilize anchor-based methods. All anchor-based approaches, or anchor box approaches, slow down the processing because there are lots of extra steps to process. With this approach, you must carefully choose the anchor box parameters and not just the number of anchors. For example, with YOLO anchor parameters, you can increase anchors to 100, but if all anchors have a height to width ratio, aspect ratio that is not close to 3:1, you'll never be able to detect people. This is actually a negative aspect compared to CenterNet, which is something we'll discuss next. As seen in previous slides, these anchor-based methods could and do result in overlapping detections. This is why you must use NMS for the post-processing after all the bounding boxes are formed. Now, regarding the last point on this slide, every SSD input dimension requires different predefined anchors, but these are difficult to accommodate for all dimensions. This is seen as a gap in working with SSD models. To establish the anchor coordinates from one dimension to another could cause a very large accuracy loss because the anchors end up being mislocated. This is a pretty challenging concept to explain in the short time we have here, so I can recommend some good reading materials if you're interested in exploring this further. One of the key selling features of CenterNet is that it uses a heat map to find object centers instead of anchors. The model still needs a framework to store the heat map center points, but it scales better than anchors because you can set the maximum number of possible objects per image, reducing computation and overlapping. Also, classification or feature extraction is straightforward because each heat map is generated along with the class. On the other hand, anchor-based methods or anchor-based models fix a number of predefined locations that will generate a corresponding number of bounding boxes. This approach forces us to execute the post-processing NMS to prune overlapping objects. With CenterNet, you still have the option to utilize NMS to eliminate some of the heat maps, but research has indicated insignificant value on accuracy improvement.
CenterNet offers a great flexibility for changing the backbone. You may prefer ResNet, Hourglass, or MobileNet feature structure depending on your performance or accuracy requirements. It is possible to use a CenterNet directly from the Model 2, but we find that the best results can be obtained by writing it from scratch and targeting a specific processing platform such as the NPU inside the i.MX AM+. So Ason has taken this approach, investing many personal months of engineers to create a customized CenterNet that is both high performance and high accuracy as well. Unlike YOLO or SSD, two-dimensional shapes can be estimated by adding one more channel to the width and height predictor. In this way, the center point will be the same in the two-dimensional view, so the model only needs to estimate one more dimension and offset for the third channel. A few other points about CenterNet, a positive point. First, as described in previous slide, the model can learn where objects are without using predefined anchors. This, of course, reduces training times and demands less preprocessing since the NMS is not required. A second point is that CenterNet works with low to high resolutions, unlike SSD, for example, which is limited to higher resolutions. Another benefit of CenterNet is the flexibility to support multitask detections. With a single pass, the algorithm can perform post-estimation, object tracking, instance segmentation, and even three-dimensional object detection. One thing to know in this picture is the mislabeling of a kite in the small object pointed out by the blue arrow. This misidentification can be improved by only applying additional augmentation settings during the training process or by simply setting the minimum probability threshold higher. Note that this house is mispredicted as a kite, but with only 41% confidence level. Also, if we look at the picture, then we realize that the small house is difficult to identify as a house even for us.
If you've already been trained on eIQ Portal, you've certainly seen these two options for development workflow with bring your own model and bring your own data. We won't go into any of the details here, but I just want to point out that this GUI and underlying tools allow you to bring in the Ozone optimized CenterNet model or any other models from Ozone for that matter, and easily do additional training of these models with your own data. In other words, whether it's YOLO or CenterNet or any model from the Ozone model pack, you can drop it in as a plugin to eIQ Portal and the tool will easily train it. Furthermore, Ozone can provide optimizations for models with unsupported operators in the base platform. If you've been trained on the eIQ Portal, You're probably already familiar with this detailed development workflow, where you can start off by choosing whether you want to do a classification or detection model, then moving on to selecting the target, which would be MCU, GPU, CPU, or MPU. You could also choose whether you want a performance or accuracy optimized model. But whether it's YOLO or CenterNet or any other model from the Ozone model pack, you can also drop this into the eIQ portal, and the tool can easily train that as well. An eIQ portal can be used as a very capable wrapper to train, evaluate, and deploy custom models from the source code. We also have a very competitive team at Ozone, constantly integrating support for optimizing new operations and models on new target devices. Of eIQ portal, I want to highlight its other benefits, and that is its ability to do quick model training, validation, and testing directly on the hardware platform. It provides a great playground to try things out, whether it's a choice of inference engines such as the DeepView RT, models, backbones, or compute units. If the target platform is plugged into your host machine, simply click on the link in the GUI and instantly deploy your trained model, whether it be your own hardware platform, an NXP EVK, or one of the Ozone starter kits. Model zoos provide models for basic evaluation of various models, including mobile nets, ResNets, SSD, YOLO, CenterNet, etc. Model zoos provide reference implementations trained on one of the common public datasets for the purpose of doing apples-to-apples comparisons. But for your own domain, how close is it to the COCO dataset? To effectively use these public models in your application, you'll have to retrain them using your own datasets. One thing to note in this photo is the mislabeling of kite in a small object. This misidentification can be improved by doing additional augmentation on the training data or to set the minimal threshold higher. It's kind of small to see, but note here that the house is mispredicted as a kite, but with only a 43% confidence level. In the model zoo with CenterNet, the focus isn't on embedded devices. Instead, they are more targeted at x86 machines with floating point support and overly abundant resources. But again, these zoo models are primarily for evaluation. What's the difference? Well, for one thing, how do you quantize it? Are the operations supported for quantization? Specifically, with the generic CenterNet model, the quantized sigmoid activation provides incorrect results, and the quantized transpose convolutions do not support per channel mode. Again, Ozone had to make pretty extensive customizations on the CenterNet model, actually creating it from scratch to deliver this high quality implementation for the i.MX 8M Plus NPU. Furthermore, to effectively use the model zoo versions, you'll also need the source code implementation to allow you to make tweaks in order to retrain it. In other words, directly from the zoo, you won't be able to train these for your own application. If you have the skills of a data scientist, it isn't rocket science work, but it does represent a fair amount of work, and Ozone has this expertise and can save you time.
As mentioned before, you can use public datasets such as VOC, COCO, or open images to pre-train the high-level features. Most detection models come pre-trained with these and require lots of preprocessing powers, so best left for the goggles to do this in their cloud machines. As always for any model, be sure to balance your dataset for equal weighting of classes and use or try to use augmentation techniques to enhance your dataset and reduce overfitting. A lot of augmentation techniques are included into the eIQ portal right now for supporting the user bringing in their own data and trying their models. As a proof of the utility of augmentation techniques, we find out that if we apply these augmentation techniques on the generic COCO dataset, the mean average precision can be increased by more than 2.3%.
This slide is pretty self-explanatory and with no surprises. As expected, the NPU of the i.MX 8M Plus delivers significantly better performance than the combined 4 A53 cores. In practice, this gap is even bigger because typically, in a real-world application, you wouldn't dedicate 100% of 4 A53's bandwidth just to run inferencing. Well, Ovis, it's been fun. Thanks for your support on this presentation. And as we wrap things up, we'd like to provide you with a few good articles related to what we discussed today. There are thousands more on the internet, so go check them out. And also check out Ozone's website for a list of the models and other enhanced machine learning tools and middleware that we provide. Contact us, we'd love to explain this stuff in more detail and determine how we can work together to bring your machine learning projects to market. Thanks for watching and listening.